Section 14.5, Temperature and Rate. The rates of most chemical reactions increase as the temperature rises. For example, dough rises faster at room temperature than when refrigerated, and plants grow more rapidly in warm weather than in cold. We can literally see the effect of temperature on reaction rates by observing chemoluminescence reactions, one that produces light. The characteristic glow of fireflies is a familiar example of chemoluminescence. Another is the light produced by silalume light sticks, which contain chemicals to produce chemoluminescence when mixed, as seen in Figure 1411. These light sticks produce a lighter bright at a higher temperature. The amount of light produced is greater because the rate of reaction is greater at the higher temperature. Although the light stick glows more brightly initially, its luminescence also dies out more rapidly. How is this experimentally observed temperature effect reflected in the rate of expression? The faster rate at higher temperatures is due to the increase in the rate constant with increasing temperature. For example, let's reconsider the first order reaction of methoisonitrile going to acetonitrile. Figure 1412 shows the rate constant for this reaction as a function of temperature. The rate constant, hence the rate of reaction, increases rapidly with temperature, approximately doubling for each 10 degrees Celsius rise. The collision model. We've seen that reaction rates are affected both by concentration of reactants and by temperature. The collision model, which is based on the kinetic molecular theory, accounts for both of these effects at the molecular level. The central idea of the collision model is that molecules must collide to react. The greater the number of collisions occurring per second, the greater is the reaction rate. As the concentration of reactant molecules increases, therefore, the number of collisions increases, leading to an increase of reaction rate. According to the kinetic molecular theory of gases, increasing the temperature increases molecular speeds. As molecules move faster, they collide more forcefully or with more energy and more frequently, increasing reaction rates. For a reaction to occur, though, more is required than simply a collision. For most reactions, only a tiny fraction of the collisions lead to a reaction. For example, in a mixture of hydrogen and iodide at ordinary temperatures and pressures, each molecule undergoes about 10 to the 10 collisions per second. If every collision between hydrogen and iodine resulted in the formation of hydroiodic acid, the reaction would be over in much less than a second. Instead, at room temperature, the reaction proceeds very slowly. Only about 1 in every 10 to the 13 collision produces a reaction. What keeps the reaction from occurring more rapidly? The orientation factor. In most reactions, molecules must be oriented in a certain way during collisions for a reaction to occur. The relative orientations of these molecules during their collisions determine whether the atoms are suitably positioned to form new bonds. For example, consider the reaction of chlorine atoms with NaCl. The reaction will take place if the collision brings the chlorine atom together to form chlorine gas, as shown in Figure 1413. In contrast, the collision shown in 1413b will have an unaffected and will not yield products. Indeed, the great many collisions do not lead to reaction, merely because the molecules are not suitably oriented. Another factor, however, is usually more important in determining the particular collisions result in a reaction. The activation energy. In 1888, the Swedish chemist Svante Arrhenius suggested that the molecules must possess a certain minimum energy for energy to react. According to the collision model, this energy comes from the kinetic energies of the colliding molecules. Upon collision, the kinetic energy of the molecules can be used to stretch, bend, and ultimately break bonds, leading to a chemical reaction. That is, that the kinetic energy is used to change the potential energy of a molecule. If molecules are moving too slowly, with too little kinetic energy, they merely bounce off of one another without changing. To react, colliding molecules must have a total kinetic energy equal to or greater than some minimum value. The minimum energy required to initiate a chemical reaction is called the activation energy. The value of E sub A varies from reaction to reaction. Figure 1413, molecular collisions and chemical reactions. Two possible ways that chlorine atoms and NaCl molecules can collide are shown. A. If molecules are oriented properly, a sufficiently energetic collision will lead to reaction. B. If the orientation of the colliding molecules is wrong, no reaction occurs. The situation during reactions is rather like that shown in Figure 1414. The player on the putting green needs to move the ball over the hill to the vicinity of the cup. To do this, she must import enough kinetic energy with the putter to move the ball to the top of the hill. If she does not impart enough energy, the ball will roll pathway up the hill and then back down. In the same way, molecules may require a certain minimum energy to break existing bonds during a chemical reaction. In the rearrangement of methylisonitrile to acetonitrile, for example, we might imagine the reaction passing through an intermediate state in which the nitrogen-carbon double bond portion of the molecule is sitting sideways. The change in the potential energy of the molecule during the reaction is shown in Figure 1415. The diagram shows that the energy must be applied to stretch the bond between the methyl group and the nitrogen-carbon group to allow the nitrogen-carbon group to rotate. After the nitrogen-carbon group has twisted sufficiently, the carbon-carbon single bond begins to form, and the energy of the molecule drops. Thus, the barrier represents the energy necessary to force the molecule through the relatively unstable intermediate state to a final product. The energy difference between that of the starting molecule and the highest energy along the reaction pathway is the activation energy. The particular arrangement of atoms at the top of the barrier is called the activated complex or transition state. The conversion of the methyl single bond nitrogen triple bond carbon to the methyl single bond carbon triple bond nitrogen is exothermic. Figure 1415 shows that the product is having a lower energy than the reactant. The energy change for this reaction, delta E, has no effect on the rate of reaction. The rate depends upon the magnitude of the activation energy. Generally, the lower the activation energy, the faster the reaction. Notice that the reverse reaction is endothermic. The activation barrier for the reverse reaction is equal to the sum of the total energy and the activation energy for the forward reaction. How does any particular methylisonitrile molecules acquire sufficient energy to overcome this activation barrier? It does through collisions with other molecules. Recall from the kinetic molecular theory of gases that any given instant, gas molecules are distributed in energy over a wide range. Figure 1416 shows the distribution of kinetic energies for two different temperatures, comparing them with the minimum energy needed for the reaction of delta activation energy. At the higher temperature, a much greater fraction of the molecules has kinetic energy greater than activation energy, which leads to a much greater rate of reaction. The fraction of the molecules that have energy equal to or greater than the activation energy is given by the expression F equals E to the negative activation energy divided by RT. In this equation, R is the gas constant of 8.314 joules per mole Kelvin, and T is the absolute temperature. To get this idea of magnitude of F, let's suppose that the activation energy is 100 kilojoules per mole, a value typical of many reactions, and that the temperature is 300 Kelvin. Around room temperature, the calculated value of F is 3.9 times 10 to the negative 18, an extremely small number. At 310 Kelvin, the fraction of F is 1.4 times 10 to the negative 14. Thus, a 10-degree increase in temperature produces a 3.6-fold increase in the fraction of molecules possessing at least 100 kilojoules of energy. The Arrhenius equation. Arrhenius noted that for most reactions, the increase in rate with increasing temperature is nonlinear, as shown in Figure 1412. He found that most reaction rate data obeyed the equation based on three factors. A, the fraction of molecules possessing the energy or activation or greater. B, the number of collisions occurring per second. And C, the fraction of collisions that have the appropriate orientation. These three factors are incorporated in the Arrhenius equation. K equals A e to the negative activation energy divided by RT. In this equation, K is the rate constant, E sub A is the activation energy, R is the gas constant of 8.314 joules per mole Kelvin, and T is the absolute temperature. The frequency factor, A, is constant, or nearly so, as the temperature is varied. The factor is related to the frequency of collisions and the probability that the collisions are favorably oriented for notation. As the magnitude of activation energy increases, K decreases because the fraction of molecules that possess the required energy is smaller. Thus, reaction rates decrease as activation energy increases. Determining the activation energy. Taking the natural log of both sides of equation 1419, we have, as shown in equation 1420, has the form of an equation with straight line. A graph of K versus 1 over the temperature will be a line with a slope equal to negative activation energy over R and a y-intercept equal to the natural log of A. Thus, the activation energy can be determined by measuring K as a series of temperatures, graphing the natural log of K versus 1 over the temperature, and then calculating E from the slope of the resultant line. We can also use equation 1420 to evaluate the activation energy in a non-graphical way if we know the rate constant of a reaction at two or more temperatures. For example, suppose that at two temperatures, T1 and T2, a reaction rate constant K1 and K2. For each condition, we have the natural log of K1 equals negative activation energy over RT1 plus the natural log of A, and the natural log of K2 equals negative activation energy over RT2 plus the natural log of A. Substituting in K2 from K1 gives us, simplifying the equation and rearranging it gives us the natural log of the first constant over the second constant equals the activation energy over the gas constant times the quantity of 1 over T2 minus 1 over T1. Equation 1421 provides a convenient way to calculate the rate constant at some temperature T1 when we know the activation energy and the rate constant K2 at some other temperature T2.